Here in chapter 6 we were looking at polar coordinates, and so then the advantage is you can transform Cartesian coordinates into polar coordinates according to these formulas. X is r cosine theta, y is r sine theta, and then of course you want to look at a function which depends on r and theta. And to do PDEs with this kind of stuff, we need to transform the Laplacian into polar coordinates, which is done right here. So let me read this. So Laplace u is 1 over r d by dr of r du by dr plus 1 over r square d square u by d theta square. And of course, this only makes sense if you really can write your function in this form as a function of radius and angle. Okay. Now if we do this, we can do separation again. So here is the separation formula. But now, of course, we separate in radius and angle. So r of r, theta of theta. Or if you have a time-dependent problem, right, we do r of r, theta of theta, time of time. T of t. Okay. And from this, doing separation, we get a radial problem, an angular problem, and a time problem. If we have the Laplace equation, we don't get a time problem. But you know what I mean. So this is the general case. And it turns out the radial problem satisfies the Cauchy-Euler equation, like given here. And then this Cauchy-Euler equation was solved by r to the n and r to the minus n. R to the minus n was removed because it is not bounded at 0. If r goes to 0, r to the minus n goes to infinity. So this goes away. Or for higher modes, we had the Bessel equation. And the Bessel equation is this here. And then this depends on the n. We didn't have the n earlier in the Cauchy-Euler. This n comes from the angular problem, right? And so then if we put this in here, we get Bessel's equation, and then the solutions are what? Bessel functions, yay! And these are the ym's and the jm's and the jm's. These were functions which oscillate like this, and the ym's were functions that came from minus infinity and oscillate like this. Ym of x and jm of x. So meaning the j's are the good guys and the y's are the bad guys. And we want to remove them again because they go to minus infinity when x gets really small. Okay, we learned a little bit about Bessel function properties, etc. In particular, oh yeah, here's one thing which we need. These are the zeros, right? So the mth Bessel function has zeros and we call them zmn. So again, let's plot the mth Bessel function. Jm, this time I call it of z. And then these guys here are the zeros of that function. So this would be the first zero of the mth function. This would be the second zero of the mth function. Here we have like the fifth zero of the mth Bessel function. And these are used, right? These are used to define our basis functions jm at zmn times x. And this will then used in a general Fourier-Bessel series to find our solutions. It looks a bit scary, but really it isn't, right? So again, like in the previous chapter as well, it's important to be able to keep track of the indices. Not mix them up, write clearly what is m, what is n. Maybe did I write clearly enough? Okay, so m is this and n is this.